Thank you for the very kind introduction. Indeed, there are many interests of the DoD in energy efficiency, and it's my pleasure to be here. I do want to extend a special thank you and appreciation to the organizing group. I've really enjoyed the last day or so, hearing some different perspectives and really engaging in a different way. It's a very effective format, and I appreciate that. Many of you associated with the university are probably very much aware of the Office of Naval Research. Very quickly, I'd like to iterate that we were established by acts of Congress. Okay? As World War I was winding down, it was Thomas Edison who said, okay, I helped you guys out during the war, but you know you really need your own laboratories. You need to keep up this momentum and you need to be prepared. That was taken on board. We built our own laboratory in Washington, D.C. Now there's 3,000 PhDs and technical folks working there for our needs. That's our corporate laboratory. Again, following another war, Vannevar Bush was charged with pulling together the team that established the Manhattan Project. Shortly thereafter, he said, okay, folks, you really need a concerted effort, a way to draw in academics from throughout the country so that they are working on your issues. And we do have a challenge. We have that resource. In 1946, the Office of Naval Research was founded. A few years later, Vannevar Bush went off and established the NSF based on the model. Most recently, and perhaps intriguingly, in 2001, we were given responsibility for applied research and advanced development. That means we're responsible from all the way up through a TRL level of 6. It's a tremendous responsibility, but it's a tremendous tool that we have at our disposal. Just in case the suit didn't already give you a glance, I am from inside the Beltway, and I feel obliged to show you an org chart. I don't know. We're supported under the command of a 2-star Admiral, Nevin Carr, very fine engineer. We're supported by ONR Global. We have reach into 70 countries. We support research in over 1,000 universities, 3,000 PIs, 1,000 businesses, 80% of which are small businesses. We have a matrix structure. I work in Code 33, Sea Warfare and Weapons. Where else would materials be? We have responsibility for the entire environment of naval applications. I want to point out Dr. Rich Carlin because he's also the S&T lead for the Navy on power and energy. It's my boss and directing a lot of what we do. We have 3 directors matrixed in that have responsibility for different parts of the portfolio. And I'll spend a little bit more time on that when we get to the next chart. But I do want to point out Dr. Michael Kastner. He's with us for just 2 to 4 years from the University of Southern California, serving as our Director of Research. What's noteworthy, I think, is that in 2009, he was given responsibility for all of the STEM work that the Navy does. And then he was asked to double that investment in 5 years. Currently, we're spending about $50 million a year with a goal of $88 million per year on STEM, not including the support that comes naturally through grants to universities for graduate students and postdocs. So a very major undertaking. I take my hat off to him. A good engineer, he stepped up and immediately looked at the metrics and looked at what was most effective. And is focusing our program really on diversity, working in urban environments, but devising programs that have high touch quality so that the mentors, the teachers are well trained and in touch with these kids after they spend a week or 2 at a camp, okay? They're with them continuously as they go along, taking advantage of our military installations, our laboratories distributed out throughout the country, and trying to engage these folks in the summer and really build up a workforce. Okay. So that's who we are. This is how we arrange our work. Very quickly, we're informed by two standard documents introduced every 2 years. The Naval S&T Strategic Plan and the U.S. Marine Corps S&T Strategic Plan. And they help us to focus our activities in 13 specific areas. Power and energy is at the top of the list for good reason. We manage this full portfolio of basic research, applied research, and demonstration work through 4 primary programs. The Director of Research is responsible for 40% of this activity. This is what I'll refer to as discovery and invention. This is our entire 6.1 portfolio, as well as a good portion of our 6.2, the applied research work. Leap Ahead Innovations, our innovative naval prototypes, are the big challenges that we undertake that are particularly Navy unique, that won't be done unless we take the first step to show what's possible. Among those are the EM railgun, okay, which is huge, huge activity. A free electron laser to use as a weapon aboard a carrier ship. And very importantly for this community, perhaps, is the long-endurance unmanned underwater vehicle, which would be used for reconnaissance, but would have tremendous requirements for mission capability and endurance at sea that really drive a lot of our power and energy activities. Quick reactions are exactly that. A good idea comes from the fleet, and we react on it. One of our sailors wrote to us and said, you know, I'm really weary of the process we use to clean the deck on this carrier. It takes a whole bunch of us. We have our mops, we have our brooms. It takes forever. There's got to be a better way. This deck is huge. It's 3 football fields. What can we do? So we modified a Zamboni. Okay, that's what we have. It looks just like a Zamboni. It goes along. It uses recycles its own water. It's very environmentally sound. And, you know, that sailor is very happy. That's, acquisition enablers, our FNC projects, are how we mature our advanced work. These are typically 4-year programs that take a technology from a technology readiness level of about 3 to 6, which means it's ready for prototyping and experimentation in a realistic environment. Now on to the good stuff. Department of Energy goals, very serious goals articulated both by the Chief of Naval Operations, Admiral Roughead, and Secretary Mabus for the Department of the Navy. We will consider energy factors in all of our acquisition processes. We will sell the Great Green Fleet by 2016. That means a fleet of ships with their aircraft working on biofuels and blends thereof. We will reduce non-tactical petroleum use by 50% in the fleet. We will make sure that as we build, our facilities are as close to net zero as possible, and we will increase our use of alternative energy sources by 50%. Okay. We salute. Okay. Yeah. So these are tremendous objectives, and they're national objectives. They're ones that the Navy has embraced. And I think it's important to think about why the Navy can embrace these. We have a lot of tools that we can bring to bear. We can target our research activities in power and energy activities. We can ensure that we're building the workforce of tomorrow by targeting a lot of our STEM work in power and energy. And perhaps more urgently, we can serve as early adopters of technology. We have bases, we have platforms where we can experiment, where we can develop technologies as they come on board, and we have control of those. Not very unlike the private community. So this is how we organize our thoughts. The Navy is everywhere. Okay, we're in space, we're under sea, we're on land, we're at sea level, and we use power all across the full spectrum. Fuel is a complicated subject, to say the least. We are not spending significant efforts in biofuel development. What we are spending our money on is to understand the fuels and to ensure that we have good understanding of how those fuels will interact with our systems, with our propulsion systems, with our storage and our distribution systems. Power generation, we're looking very seriously at fuel cells for a number of reasons. Propulsion systems, all forms of energy storage, including higher energy density capacitors, which you have not heard much about in this conference. Distribution and control, silicon carbide switches, intelligent distribution systems that enable us to really take advantage of the power supplies that are coming on board. And very importantly, I think the power loads and where we can impact just how much fuel we're using, whether it's in the design of a rotor blade or a radar system to allow us more fuel efficiencies. Okay. Unmanned systems, wonderful, wonderful platforms. They can go nearly anywhere. They don't put our sailors at risk, our Marines at risk. Wonderful platforms for playing with new technologies, okay? Wonderful transition opportunities and experimental space. Very proud of the Iron Tiger, developed at the Naval Research Lab, 550-watt fuel cell system. Total weight of the system, about 35 kilograms, 5 kilograms of payload. She sailed for 26 hours in November 2009. Later this month, in May, she will be tested for 72 hours of endurance. Noteworthy, she survived 40-mile-an-hour winds with 60-mile-an-hour gusts during that 24-hour deployment. Beautiful little system. Unmanned undersea vehicles are challenges, like the air versions of our power requiring systems. All of these systems have to be very small. They have to be as lightweight as they possibly can, very high energy, very high power density requirements. If you're working underwater, then you also have to be neutrally buoyant, okay? We need to make the design as simple as possible. We need to be depth independent, okay? So that means that our fuels that we carry on also have to be able to be contained in a depth independent way. Many, many opportunities in that regime. Two of our major programs, okay, one of those FNC, Developing Mature Technologies, is looking at power capabilities for an unmanned vehicle that could be deployed from a torpedo tube. That means you're working with a diameter of 21 inches, a very challenging small space to work in. The IMP associated with this, more major challenge, is again looking for an unmanned vehicle but with more stringent requirements, mission capabilities that would require 80 days at sea, okay? Various combinations of idle, slow transport, rapid transport, communication systems. We imagine that in order to meet our requirements, we will need 3,000 watt hours per liter by 2018, okay, to meet those goals. And so underlying all of this is a strong history of working in fuel cells. What I do want to show in this chart is the work on the Raman spectroscoper, the Raman spectrometer in the upper right corner. While we work all the way from very first principles, understanding what's happening at the nanoscale, at the surfaces and interfaces of the various components, how the oxidizers and fuels are working, interacting, we're also working on the tools to let us understand that better. That image showed up on the Journal of Electrochemistry about 2 years ago and actually allows us to look in situ at some of these reactions that are occurring at about 700 degrees Celsius. We work on batteries. It's a smaller program. We're relying very heavily on what's emerging in the private sector and under DOE support. Our interests are really focused at this time in understanding failure mechanisms, understanding the limitations of charging and recharging, and how to design safely for these systems, which will be ubiquitous. In many of the hybrid power systems that we're imagining, there will be some role for batteries, and we're trying to understand how to do this as well as we can. Expeditionary portable power was alluded to earlier by John, and with good reason. When the Marines or our expeditionary forces go out, a large part of where they meet risk is in transporting fuel to their forward operating bases. Those convoys are large, they're steady and regular, and they're predictable, and they're incredible targets for insurgents. So we're doing everything we can to give them the tools so that they need fewer of those convoys. Very proud of Greens. We just developed that in 18 months. A man-portable device capable of providing about 300 watts on a continuous basis. Okay, just set it up, and a combination of fuel cells and batteries gives the Marines enough energy to charge their batteries in the field. We continue to work on photovoltaics, specifically for these sorts of applications. Bless you if you're a communication specialist in the military. In addition to your regular gear, you're going to carry another 60 pounds of batteries just for those communications. What we'd really like is a simple photovoltaic system that we can roll up, slap in the backpack, charge our batteries. That's cheap enough that if we need to leave it behind, we can leave it behind. That's where we're shooting. All of these fuel cell systems on this chart for our Marines are operating on JP8, bringing a number of technical challenges associated with reformatting and avoiding contamination, but working in a realistic environment, we need that capability. Photovoltaics, wonderful program managed by Paul Armistead. Looking at polymer heterojunctions, various effects, trying really to design materials for each opportunity within the photovoltaic cycle, specifically for that need. And then to devise processing routes that are affordable, that aren't fighting thermodynamics, and exploring some very clever opportunities in self-assembly. We continue to work on the processing of these technologies and hopefully meeting roll-to-roll manufacturing goals. I tossed this in as an example of where we can be an effective early adopter of technology. High-temperature superconductivity is a tremendously advanced technology, very, very few applications in real terms. We've supported this work throughout the 70s, but most importantly, doing a lot of the fundamental work on the BISCO system in the 80s to understand this phenomena and produce it. When the second generation of high-temperature superconductors came online, they're operating in about the same performance space, but they're so much more affordable to produce. Okay, these are layered structures. We know how to build those tapes. What we didn't know how to do is how to wind those tapes, how to understand the mechanical behavior of these systems and how to optimize for that. And so we spent a good amount of research and development specifically on understanding the mechanical properties and how they affect the transport properties. And we found a wonderful application. The USS Higgins was fitted with over 100 meters of second generation high-temperature superconducting cable. The images here show the difference between using the traditional copper cables and using high-temperature superconducting cables. Even when you consider all of the balance of plant, the extra cryogenics, the compressors, the cryostats, you save 50% of the weight by switching to this system. it's more efficient, and you know what? It's a tremendous, tremendous acquisition cost saver, because pulling those cables through the bowels of a ship, drilling holes to support them, is a hard, time-consuming job that requires a lot of simple labor pulling, because you're working in very awkward areas within the bow of the ship. So for degaussing, which we do and which we need to do as we enter a littoral space, someplace where we might imagine mines being set for us, this is a tremendous advantage, and one that we'll continue to pursue. We do work propulsion materials. I want to call out that we work all the way through the development of an engine, but all the way back to the first principles. And here I'm very proud to point out to you these images in the lower right. A lot of very, very good work done right here at UC Santa Barbara and Amiri, headed by Tony Evans, to understand the failure mechanisms of the thermal barrier coatings that we use to give us extra temperature capability, extra efficiency within that propulsion system. This is important in traditional environments. This gives us greater operating range, greater efficiency, much higher temperature operation. In a sandbox, it also gives us incredible opportunities for reducing maintenance. Primary cause of failure of these engines are degradation of those thermal barrier coatings from what we call sea mass attack. Essentially, the sands in the desert will be ingested by the engine, okay, which is it's a giant vacuum cleaner if you look at it. And those glasses will react with the thermal barrier coating, breaking it down very, very quickly. Understanding that was developed here at UC Santa Barbara is enabling us to build better thermal barrier coatings that can withstand that and can withstand other applications. Okay. Anti-biofouling coatings, structural weight, lightweight structural materials, all technologies that feed into that last realm with considering power loads. If you can take 10% of the weight out of our systems, you can save perhaps 6% in the cost of transporting them and moving them through water and moving them on land. If you can reduce the amount of biofouling in a controlled way, there are estimates that you can save as much as, well, if you had a perfect coating, you could save as much as 6% in fuel efficiency just by having that low friction. I don't think we'll ever have a perfectly pristine coating on a ship. Okay, this is a Navy ship after all. But could we reduce the fuel consumption by 3% through some of these technologies? I'm certain we can. Desalination systems, updating our technology base, using more mature membrane technologies, designing the systems better. We're achieving 40% reductions in weight and volume and 60% reductions in fuel consumption. And with that, I think I'm in trouble because I've already gone over. But I do want to leave with you where we see our role in solving this problem.